A fast food outlet claims that the mean waiting time in line is less than 3.5 minutes. A random sample of 15 customers has a mean of 3, so we already have the data here, all of the data. We have the null and the alternative hypothesis. This is how we could have done this without using the p-value. I'll show you the technique. So we have HO and we have HA, mean is greater than or equal to 3.5, mean is less than 3.5, and that's the claim. We have X bar, guys, which is 3.4. We have N to be 15. We have S to be 0.6, and we have alpha 0.05. Okay, what is the critical value approach? I'm going to explain it right now. So this is step number 1. Step number 2, critical value approach means you're not using the calculator. You're not just to do the work, just doing it by hand. Step number 2 is to find the test statistic, which you've been finding using the calculator, and it is called T. If you remember yesterday, guys, I gave you a formula for Z, which was X bar minus the mean divided by sigma over square root of N. And the formula for T, guys, it's very much the same. It will be X bar minus the mean, but instead of sigma, guys, we just use S because we don't have sigma, we have S. So that's the formula for T. If I am to do this by hand, here's how I do it by hand. It will be 3.4, that's X bar, watch. Minus the mean, we pick it up from the null hypothesis, which is 3.5, divided by S, which is 0.6, over square root of N, square root of 15. And you guys, we already used the calculator and did the work. I know the answer is negative 0.646. Okay, this is the step now that is different from the p-value. It's called the critical value approach. Let me show you how that works. This is a normal curve. It's a T curve. This is a left. Okay, can you guys tell me whether you think this is a left tail test, a right tail test, or a two tail test?
A left tail test.
I agree. It is a why? Because this is less than. So you'll come and shade just this area to the left, right here. Since this is a left tail test, this curve is split into two pieces. In one piece where we reject the null hypothesis, this is called the rejection region, and this is called the non-rejection region of the null hypothesis. And this is the number line, and we know that this is 0, guys. Okay. The critical value, guys, if you remember from confidence intervals, when I say 90% confidence, I put 90% in the middle, and I said there are 10% split up, between the two tails, 5 and 5, and we found two critical values. One is negative and one positive. This is exactly the same critical value I'm talking about here. Now, this critical value here, guys, for me, in order to find, I need to know alpha. And alpha is given here to be 5% in the problem, 0.05. So to find the critical value, you need alpha, which is a 0.05, and that's actually what I shaded. And the critical value is a number for which the area to its left is 5%, and I need to find this number. When we did Z, guys, we found this number using the inverse norm. When you do T, actually, the calculator has a feature would allow us to find a critical value. It's called inverse T. Or we can use table 5, just to find this value. Let me just get the table and show you what I'm talking about right here. Okay. So what would this value be, which is called the critical value? If I had a right tail test, guys, I would be shading this to the right. But since I have a left tail test, I'm shading it to the left. Remember, alpha is 0.05, guys, and N is 15. Let's look here. It says one tail alpha, that's 0.05. So I'm good here. Now I need the degrees of freedom. If N is 15, what will be the degrees of freedom, guys? 14, and watch. Where is the one tail alpha, or the second one? 1.761. But because I am on the left, guys, I just put negative 1.761. This number, guys, the negative 1.761 is called the critical value. And this number splits up the two regions, one to a non-rejection region and one to a rejection region of the null hypothesis. And this is negative 1.761. Now we need to make a decision whether we should reject the null hypothesis or fail to reject the null hypothesis. Remember, guys, we ended up failing to reject the null hypothesis. Let me show you how we do it with the critical values. You see the negative 0.646. I would like you to put it on the number line. Do you guys agree with me? If I put this on the number line, it will be somewhere here. Below 0, but above negative 1.761. So it turned out not to be in the rejection region. You see that negative 0.646 is not in the rejection region, then you fail to reject the null hypothesis. If this number, guys, let's say it was negative 2.6, it would have been here, because below negative 1.7, then you will end up reject the null hypothesis. So critical values, you compare a number with a number. P-value, you compare a probability with a probability, because alpha is a probability and the p-value is a probability. It's just like you either compare an apple with an apple or you compare an orange with an orange. So this is what the critical value approach is. And as I told you guys, this value, the negative 1.761, you could have found using the calculator, using what we call inverse T. Let me show you the inverse T here. Second and distribute. You can see number 4, inverse T. It requires the area to the left of the target, which is alpha. So I use 0.05. And the degrees of freedom, guys, which is 14. And I should get negative 1.761. Watch. There you go. That is the same thing as using the table. So this is pretty much it, just about the critical value, guys, just to give you an idea of what critical values are. You can use the table to find the critical values. All you need, guys, to identify alpha and whether you have a one tail or two tails. If you have two tails, you just use the third row. If you have one tail, just use this row. Pick up alpha, pick up the degrees of freedom. You can find the value here. If your test is a left tail test, make sure to put a negative sign next to the number. If it is a right tail test, just use it as is. So this is for the critical value approach. Now for section 7.5. It's about testing claims about standard deviation or population standard deviation or population variance. Let me just walk you through this section for a little bit. All right. So this is what the section is about. Testing hypothesis for variance and standard deviation. So you could be like, for example, you could be answering a question, test the claim that the standard deviation is less than 15. And here's how you would state, just the claim. Since we're talking about standard deviation, guys, you cannot use this and you cannot use that. Those signs are not used anymore. You have to use sigma. Sigma less than 15, sigma greater than or equal to 15, and that's the claim. Or you could answer a question, test the claim that the variance is more than 50. Variance, guys, as you learned in chapter 2, has a sign, not sigma, sigma squared. So you could be answering this claim, more than 50, and then this one will be less than or equal to 50. So this is the kind of hypothesis tests that you do in this section. Now, do we use a z-test, t-test, a proportion z-test? None of those, because the z and t tests are used to test the claims about the mean. The proportion test is used to test the claims about the proportion. And there is a new distribution that I'm going to introduce right now that we use to test the claims about the standard deviation. This new distribution, guys, is called chi-square distribution. I'm going to show you a visual of it. It looks like this. And we label it as chi-squared. What do you notice, guys, difference between the Z and T distribution? This is the Z distribution. This is the T distribution. What's one obvious difference, guys, between the two distributions?
It's not normally distributed.
It's not normally distributed. It's skewed to the right. Very good. It's not bell-shaped. Another observation, very important observation.
You're starting at the 0.
Very good. You don't have negative numbers in this distribution. And look, what's the name of it? What does it say? Chi-square. When you square a number, guys, whether it is positive or negative, what does it turn to?
Positive.
Positive, always. So this chi-square distribution, guys, is always a positive distribution. It's always shifted, just toward the right. As you change the sample size, this curve, it changes. As you increase the sample size, this curve will level off and will become like a bell-shaped. But in general, it is a right skewed, just distribution. Total area under the curve, guys, is always equal to 100%, just like, the other distributions. What I'm going to do, guys, I'm just going to do a complete exercise showing you how to do a hypothesis test, and I'll give you something similar to it, just on the test. So let me just do a complete exercise showing you how to work this out. There is no program on the calculator that will do this test for you, so we're just going to do it by hand, but you'll see it's not a difficult one. So I'm going to do example 4. So you can pay attention to this example. Could have something similar to it, just to do later. Watch. 5 steps, guys. Just like we did before, we're going to perform the 5 steps. Okay, I'm going to hide this. Your solution is already there. So I'm doing it page 397, example 4. A dairy processing company claims that the variance of the amount of fat in the whole milk processed by the company is no more than 0.25. Can you guys help me state the null and the alternative? What is no more?
Less than or equal to.
Okay, you agree. And what simple goes here? You have 2 choices, either this or that. This is for standard deviation. This is for variance. So he says variance, so I'll just put this. And that's the claim. Okay, we finished step number 1. You suspect this is wrong and find that a random sample of 41 milk containers, so N is 41, has a variance of 0.27. That's the sample. The sample variance, guys, is called S squared. At alpha equals 5%, is there enough evidence to reject the claim? When he asks you if you can reject the claim, be sure that the claim was in the null hypothesis. The question of rejection is only given when the claim is in the null hypothesis. Alpha is 0.05. Okay, let me show you what the new steps that you'll be learning here. So step number 1, something we've done already. Step number 2 is find the test statistic. And let me give you the formula. You'll be provided with a formula for this one. We call it chi-square. So it's not a Z and it's not a T, guys. Neither one. It's called chi-square. It's this formula. So you have to do it by hand. There is no program on the calculator that does this. So equal. N, guys, is 41 minus 1. Okay, can you help me, guys? What do I put for S squared?
0.27.
Okay. And what do I put for sigma squared? We assume that the null hypothesis is true until proven otherwise.
0.05 squared.
Yep, 0.25. Okay. I think I can cheat here and get the answer. It's 43.2. Okay, I'm gonna go slow with this one, guys, just to make sure you pick it up so you can do something similar. 3, look what you do for 3. You draw the curve. We're gonna use a critical value approach here. You draw a skewed curve just like that to the right. You put a 0 there. You put a chi-square. And since this is a right tail test, guys, you shade an area to the right like this. This is the rejection region. And this is your critical value here that we're gonna find. CV means not the critical value. They call it in the book chi-square sub-0, which is a critical value. I'm gonna show you how to find this critical value. This critical value will split up the curve into 2 pieces. One region, non-rejection region, and this region is the rejection region of the null hypothesis. And then once we identify this value, guys, we'll bring this and put it in the number line. If this 43.2 end up here, we reject HO. If it end up there, we fail to reject HO. How do we decide? We need to know this number. So whether to place this to the right or to the left. Now, how to find this number, guys? It's very easy. We're gonna use a table called table 6. It's called chi-square distribution, guys. And table 6 is designed to be a right tail table. And we have a right tail question, so it's perfect. It's just gonna go along with us. All we need, alpha and the degrees of freedom. He says alpha is 0.05, guys. And what are the degrees of freedom? 41 minus 1 will be 40. Watch. Alpha, 0.05. And degrees of freedom is 40. Where is the 40? Right here. So you guys agree it's 55.758. All right. Now, guys, come and put 43.2 on the number line. Would you guys agree with me that 43.2 should be to the left of 55, somewhere here? This is chi-squared. Remember, this is the non-rejection region. So what would be our decision? Our test statistic fell in the non-rejection region. Fail.
To reject.
Exactly. And you guys, you know the rest of the story, how to write the conclusion. 5. There is not, I'm going to be consistent here, enough evidence at the 0.05 level of significance. The claim is in HO, guys. So what's the magic word that I have to use here? There is not enough evidence to reject the claim. Step number 5 is about the claim. We're saying we cannot reject the claim, and that concludes the question. Before I let you go, guys, if this was a left tail test, and you need to find, just so then you will shade somewhere here, and you need to find the critical value. How would you do it? Let's say alpha was 5%. How would you do it using this table? Please remember that this table is designed to be a right tail table.
Would you just use a negative?
No, there are no negatives, remember.
Yeah, because you said this table is mainly for right tailed.
Yes. So what would you do?
1.
Yeah, this is 5% right here. When it is on the left, you do 95%, because if there is a 5% on the left, there will be 95% on the right. So you just see, did you notice here that he had a 95% somewhere? You can use a 95% and 40. But for this question, it turns out to be a right tail test. You just use it as is. So I will stop here, guys. I think you've had enough of me talking about